Hello and welcome to this review of trigonometry. Today I'll be talking about where trigonometric functions come from, how they're related to the unit circle, and we'll just do a basic trig review, right? I won't go into inverse trigonometric functions. Maybe I'll do a video on that eventually, but this will just be a review of the basics of trigonometry. So where do trigonometric functions come from? Well, trigonometric functions, they relate angles. Oh, let me actually grab a different pen. Here we go, a pencil, that's a bit nicer. And a little bit like that. Well, trigonometric functions, they relate angles. So angles to lengths or side lengths or something like that. So length. And throughout this video I'll probably be using theta as an angle, or maybe alpha, so just some Greek letters. That's a bit of a convention, if you will. And lengths are maybe x or y or s or something like that. Alright, so well, angles and lengths, so in what context should you see this? Well, they have to do with triangles, and more specifically right triangles, where one of the angle is a right angle. Right, so we have this triangle, and let me actually name a few things here. So this will be side A, side B, and by the Pythagorean theorem we can say that this hypotenuse, if you will, I'll call it C, and then we know that C is a squared plus b squared, and then square rooted, obviously, like that. Alright, so let's say actually we have a triangle like this. So we have this, and we know that this is 2. We know it's a right triangle, and we know that this angle is 15 degrees. It's not really, it's a bit more, but it's just for this purpose, right? And we say that this angle is 15, and we have a side length of 2. And say we want to know this C, right? Well, we could try to figure out this B first and then use the Pythagorean theorem, but then we have to figure out B, so we're kind of stuck, right? So this is where the trigonometric functions come in. So trig functions, because we have a side length and an angle, and what we can do is we can actually say that the sine of the angle, so the sine, sin, of this angle is the same, actually equal to the opposite side, that's a side length of 2, divided by the hypotenuse, right? So C. We say this, and sine of 15, well, I don't know what that is, but it's some number, right? You can just plug it into your calculator and it will give you some number, which means we can actually solve for C. So I'll multiply both sides by C, that will give me C times sine of 15 equal to 2, and then I'll divide both sides by sine of 15, both sides like that, and then I get C is equal to 2 divided by the sine 15, like that. And that, if I plug it into my calculator really quickly, that's gonna be 7.27, something like that, 7.3. And that it kind of corresponds. I didn't draw this properly, so it's a little bit shorter here, but it kind of corresponds with what you'd expect. Obviously, the hypotenuse is longer than one of the other lengths of the triangle, and this always holds true. So I'll just write it a bit more generally here. Right, so say we have a right triangle like this, and we have sides C, A, and B. Then the sine of angle theta right here is going to be, well, what did we do? We divided the opposite side by the hypotenuse, so that's B divided by C, like that. How nice is that? That's pretty good. Now it isn't an exact answer. Now I'll come back to when you can get an exact answer for sine of theta. For example, sine of 30 has an exact value, but I'll get back to that eventually. But I'm just showing you, where do these come from? Well, these just come from this, right? They come from relating the angle to a side length. And sine isn't the only trigonometric function. There is another one that I will tell you about, and that is the cosine function. So cosine of theta, and it's pretty much doing the same thing as sine theta, except with a different side. So whereas with sine of theta we took the opposite side, with cosine of theta I'll actually take the adjacent side. So that's going to be a, and then I still have to divide out by the hypotenuse. Divide by c, like that. And that's the cosine, right? So now these are all nice, but say for example I have a problem like this. I will use many examples because I think that's the best way to learn. Also practice these problems if you can. Alright, so say I have this is 2 and this is 3, and I want to figure out this angle theta. Because like I can, and by the Pythagorean theorem, this will be 2 squared plus 3 squared plus 3 squared. That's going to be 13, which means this side length is the square root of 13. Alright, so I have a couple of equations that I can write down according to these formulas, if you will. I know that sine of theta is b squared, that's going to be the opposite side, that's 2, divided by the hypotenuse, that's square root of 13. There we go, square root of 13. And then cosine of theta is going to be the adjacent side, 3 divided by the hypotenuse, square root of 13. Alright, but I'm still no closer to getting theta. And now I will quickly talk about the inverse trigonometric functions, because there exists a function sine -1 of theta or x or something. That's actually the inverse of sine. So if you have something like this, you do first of all you apply the sine to some variable x, and then you apply the inverse sine or the arc sine or the inverse sine. Then you get back the original thing. Right? So if I do my inverse sine on both sides here, so I'll do the inverse sine like this, and then I still have sine of theta in there, and then do the inverse sine on the other side as well, 2 divided. Then these two, the inverse sine and the regular sine, they will cancel, and I'll just be left with theta is the inverse sine of 2 divided by square root of 13, like that. And this, again, you can just plug into your calculator. It will be 33.69. Alright, 33.69, nice. And that's actually quite a reasonable answer, if you will. So it's always good to check that your answer actually makes sense by making a little sketch or something. Alright, so, and again, sine is not unique in having an inverse. You also have the inverse cosine. And then if you apply that to some cosine, you will just get back the original thing. Alright, here we go. Like that. So this is basically where the trigonometric functions come from. They come from relating angles and lengths inside a right triangle. And so now I will explain the last trigonometric function that I will cover today, because it's kind of less important. The rest are kind of, for example, you might have seen secant of x, but that's just 1 divided by the cosine of x. So I'm not going to cover that, because I don't think it's as important as the regular sine and cosine. But what I will cover is another function called the tangent of x, or actually I have tangent of theta. That's a bit better. Alright, so we have, let's just sum it up quickly. We have a function sine of theta that relates, here this is theta, that relates the opposite side to the hypotenuse. Like that. We have cosine of theta that relates the adjacent side to the hypotenuse. Like that. But now, say I don't know the hypotenuse, and I don't want to figure it out by Pythagoras, right? Because I'm lazy or something. You know, it's like that. All right. So I don't want to have this C in here, and I want to just have something with A and B. What I can do is if I have B divided by C and then all divided that by A divided by C, and I multiply both the upside and the downside by C, then this is just A divided by C times C, so those two will cancel. Same up here, this will cancel. I'll just be left with B divided by A, like that. And what I've done here is I've divided this part by this part, so I could also just say that B divided by A is equal to sine theta divided by cosine of theta. Now, it looks like I've done nothing here, but actually this fraction, sine divided by cosine, has a special name. It's called the tangent of theta. Sine of theta divided by cosine of theta. And that is equal to B divided by A. Like so. So say I have, let's do a quick example here. I have theta, and I have 1 and 3. Then I can say that the tangent of theta is, well, B is the opposite side, that's this side, that's 1, and then I have to divide by the adjacent side, that's 3. And also the tangent also has an inverse function, so I can say that theta is the inverse tangent, like that, of the tangent, the inverse tangent of a third, which comes out to be, let me quickly plug that in. No, that's alright, so that I'm not sure what my calculator is doing. Oh, I did it wrong, like that. That comes out to be 18 degrees, roughly. Alright, so now we've covered sine, we've covered cosine, and we've covered tangent, and how they relate to triangles. But really what you most often hear is that trigonometry isn't about triangles at all. It's about circles. So how do circles come into play with this? Well, I'll tell you right now. Now let's say, now what we're going to do is we'll look at, first of all, what is a circle? What is a circle? What is a circle? Well, a circle is the set of points that have equal distance to some midpoint, right? And that distance is the radius. And I can actually put this into an equation, kind of by Pythagoras, has to do with Pythagoras. If I have a point x, y, and it sits on the circle, then I can say that x squared plus y squared, like so. If, say, the midpoint is the origin, right? Then I have a point xy here, and the distance from the origin, well, that's just Pythagoras, because this is x, this is y, so this distance will be x squared plus y squared, all square rooted. And if the point is on the circle, that means that this distance must be equal to the radius. And so more often you'll see this squared out, so both sides squared. That means that the equation for a circle is x squared plus y squared equals r squared, like that. And that means that the midpoint is at the origin at 0, 0. Alright, so now we've defined a circle, right? A circle is all points that kind of that kind of have this formula, right? Where you can plug it into the formula and it works out. So what I'm gonna do, and it's gonna look a bit out of left field. I'm gonna actually create a point sine, or rather cosine of theta, comma sine of theta. So cosine is my x component, and sine is my y component. And I'm actually gonna try to plug it into this formula and just see what happens, basically. Alright, so that will give me cosine squared, the first part, and the second part will give me sine squared. Also, quick side note with the inverse, inverse sine. This doesn't mean 1 divided by sine as you may expect, because this is actually sine squared. But be wary of that. When you see this -1, that doesn't mean 1 divided by sine. That means the inverse, right? So sometimes you'll see people, to get around this, you'll see people writing a sine of theta. You can do that, but on calculators you usually see a -1. But that doesn't mean the reciprocal, right? So be wary of that. Alright, so let's head back to where we were. Yeah, we were plugging in this seemingly random point into the formula and see if it equals some r squared. Alright, so cosine squared. Well, what's that going to be? Well, I don't really know much about cosine, but what I do know is that, if I have a look up here, cosine is equal to a divided by c. So let's just plug that in. A divided by c, and still squared. And similarly, sine is equal to b divided by c, all squared. Still equals some r squared. So I'm just trying to plug it in and see if I get something. Maybe I don't, maybe I do. We'll just see what happens. And now remember, because these a, b, and c, they're actually just lengths of a triangle, I can say that c is equal to a squared plus b squared, square rooted. So I'll just multiply this out like that. I'll just distribute the power. B squared divided by c squared, like this. And then I can say that c squared is a squared plus b squared, right here, by Pythagoras. And I'll plug this into here. So I'll get a squared divided by a squared plus b squared plus b squared, a squared plus b squared equals r squared. Alright, so now I have two fractions with the same denominator, which means that I can just add the top bit, which will be a squared plus b squared, and now keep the denominator the same, a squared plus b squared, and that equals r squared. But look what we have here. I have two of the same, I have a fraction with the same, the upper part and the lower part, which means that if I say, for example, say I have 5 divided by 5, that just equals 1. 3 divided by 3, that equals 1. X divided by x, that equals 1. So this will just equal 1, which means I have r squared equals 1, which is r equals 1. So a point like this actually sits on a circle with radius 1. So I'll take that here. So point on circle with r equal to 1. Right, so let me sketch it out real quick, like that. Alright. So it's going to be, for example, our sample point, cosine of theta comma sine of theta. And that equals, this part always equals 1. And now we can see that the x part, like the x coordinate, is cosine of theta, and the y coordinate is sine of theta. And now it's kind of, where does this theta come in, right? Because it kind of, when it changes, the point kind of walks around the circle like this. Well, actually, theta is this angle right here, inside the triangle. So I'll blow this up a little bit like this. So you have theta, and then you have 1. This is still the radius of the circle, right? You have the y coordinate. Y coordinate is sine of theta, and the cosine is the x coordinate, and kind of the circle goes around like this. Alright, so this is the way that the trigonometric functions are related to circles, because kind of when you have an angle of the x-axis, they give you the resulting point on that circle. Alright, so that was quite something. So now what I'll talk about is a new way to measure angles. So what we've done previously is we've said that angles, right? Angles are in degrees, right? Degrees. I'll write that DEG like that, and that's 90 degrees, 45 degrees. You know the drill. It's pretty basic stuff. But now actually there's a bit of a more natural way to measure angles using the circle with radius 1, also called the unit circle, like this. So say for example, because it has to do with the circumference of the circle, so circumference C is going to be, well, that's 2 pi times the radius, and the radius is just equal to 1 because we're working with the unit circle, so the circumference is just 2 pi, like that. And actually, what we can do now is we can measure angles in how far we've walked along this circle. So say I am right here, now, and I measure this angle, then I've walked roughly 3/4 pi, right? Because I've walked kind of, I've walked 3/4 of half a circle, and a full circle is 2 pi, which means I've walked 3/4 pi, like that. If I were here and I've walked all the way this, then I've walked 3/4 of the circle, and the entire circle is 2 pi, which means I have walked 3/2 pi. And actually that measure will become the new angle. So for this one, that's going to be the angle. And say I have this one's pretty easy, like that. So I've walked a quarter around the circle, so a quarter, and then the entire circle is 2 pi, which means that my new angle is going to be pi divided by 2. But you already know, you can pretty much guess that this is 90 degrees. So 90 degrees corresponds with pi on 2. And what do we call this? We don't call this degrees, we call this radians. Radians. Like that. So that's pi on 2 radians. And I can also, and 180 degrees, half a turn, that is pi radians. Actually 45 degrees, that's going to be, well, it's half of 90 degrees, so that's going to be half of pi on 2, which is pi on 4 radians. And for the remaining bit of this trigonometry introduction, I will only be using radians, so make sure you get how they work, because it's kind of important. You'll only pretty much be working in radians from now on when you're using trigonometric functions, unless you're doing some kind of angle calculation in a triangle or a geometric figure like that. So radians, they are what many call the most natural way to measure angles. Right, so now previously I talked a little bit about exact values for sine, for example. I said that sine of 30 degrees, which corresponds with sine of pi on 3, pi on 6, there we go. That has some exact value. So what do I mean by that? An exact value. Well, when you plug this in your calculator, you're not going to get like, well, you might actually. Here we go, pi on 6 in my calculator. That gives me, actually I should put it in radian mode now. That actually gives me a half. Would you look at that? So how nice is that? So also, yeah, if you're doing things with radians, make sure your calculator is in radian mode, because otherwise you'll just get nonsense, because it thinks it still should measure degrees, which it shouldn't. Alright, so pi on 6 is actually equal to a half. Where'd that come from, right? Well, I won't show the entire derivation here, but there are certain values for sine and cosine that have like an exact answer like this. So another one is cosine of pi on 4, which is just 45 degrees, right? So that will be like an eighth of a turn around a semicircle. So that'll be 45 degrees, or pi on 4. And actually the cosine of this is the square root of 2 divided by 2. And you can actually plug in both of these, so you can plug in cosine of pi on 4 and the square root of 2 on 2, and you'll see the same decimal expansion, like so. Alright, so these, and I'm kind of pulling these out of thin air right now, but there's actually a nice table, or a nice table, there is a table that most trig students should learn, right? So actually I won't put it in the table, I'm going to put it right here. There we go. Alright, so, and I'll actually put these up as coordinates. So remember the x coordinate, that's going to be our cosine, and the y coordinate, that's our sine, like so. Alright, so at 0 degrees, I'll put this 0 radians rather. Well, 0 degrees also, but 0 radians. That's fairly easy to figure out. That's just 1, 0, like so. And then, as we saw, we can put in 45 degrees, like that. So that's pi on 4. And that is, well, the x coordinate is square root of 2 on 2. And it's fairly straightforward, because this is a kind of a straight line, right, with 45 degrees. That the y coordinate is the same. So that's also square root of 2 divided by 2. And I can actually put in the pi on 6 right here. Pi on 6. That's, well, the x coordinate is actually the square root of 3 on 2. And the y coordinate, which we already saw, that's going to be a half, like that. And then I'll put in another ray, like that. Pi on 3. That's actually just these coordinates of pi on 6 just swapped around. So this is going to be half. That's going to be square root of 3 on 2. And this one at pi divided by 2 radians. That's again fairly easy to figure out. That's 0, 1. Alright, so those are the exact values that you should maybe, okay, I would recommend just having them somewhere so you can always figure out the exact values of something. So I'll give you a quick example of how this works. So say I have cosine of pi on 3, and I want to figure out what is its exact value. I go to the ray of pi on 3, and I look at the x coordinate because I'm using a cosine. So this is going to be a half. If I were to say have sine of pi on 4, I'd go to the pi on 4 ray, and I look at the y coordinate because that's sine, and that's going to be square root of 2 on 2. On 2, like so. And that's the way you kind of use this table. Alright, so I have one last question. The tangent of, let's say, pi on 3, what's that going to be? Well, if you remember the tangent, we actually derived the formula earlier. That's going to be sine of pi on 3 divided by cosine of pi on 3. So you can just figure out the value of the tangent by looking up the value of the sine and the cosine. So sine, let's first of all look that up. That's going to be the y coordinate of this ray. That's square root of 3 on 2. And the cosine is a half. So that's a half. And multiplying these both sides by 2 gives me just the square root of 3. So the tangent of pi divided by 3 is the square root of 3. Really nice. And there are definitely other exact values, but they're a bit less common, and you can derive them most often by these exact values. Alright, so now that we've done these exact values, we can actually look at equations like the following. So these are what you call trigonometric equations. I'll trigonometric, like that, equations. trigonometric equations, and they are equations like sine of x equals sine of 2x. No, wait, that's a little bit too complicated for now. I'll keep it simple. Equals square root 3 on 2, like that. So what's x gonna be, right? I mean, we can take, as we did previously, we can take the inverse sine on that side, and that will give us the answer, but it won't be expressed exactly, right? We still don't know. It will be like 0. Blah. I don't know what that's gonna be. So I'd much rather have an exact answer. Well, what I can do is I can actually use this semicircle again, this quarter circle rather, to look up at what value for x, or at what angle, does the y coordinate equal the square root of 3 on 2. Let's look that up. So the y coordinate, so here it's half, here it's square root of 2 on 2, and here it's square root of 3 on 2, like that. And that's at the rate pi divided by 3. So that must mean that x is equal to pi divided by 3. How nice. And actually, right now I'll introduce a little bit of a technical detail, because if you have a quick think, if I go an entire thing, kind of an entire rotation around the circle, and I come back to pi on 3, I can say that because I can add 2 pi, which is an entire rotation, to my angle, pi on 3, and that will leave me basically at the same point. So, and I can go 4 pi around, I can go 6 pi around. So what I can say is that I can go k times 2 pi around the circle, and that will leave me with the same point, right? So I'll quickly copy that. So 2 pi times k, and then k is just some whole number, right? So it's going to be -2, -1, 0, obviously, 1, 2, and so those are all valid solutions to this equation. Alright, so basically you can always add 2 pi times k, because if you go 2 pi around, that means an entire circle, and you just end up where you were, which means that that is a valid solution too. Alright, so let's look at another equation so you get the gist. Another equation, let's say cosine of x equals negative square root of 2 on 2. So this one is a little bit more complicated because we have this negative sign, right? And this negative sign, you're not going to find negative square root of 2 on 2 in this diagram, because for that you actually need a bigger diagram, which I'll quickly draw here. So you actually need a bigger diagram like that. Alright, because right here we're only considering half a circle, or about a quarter of a circle, but actually there's an entire circle we should be aware of. So we know these values, right? But again, we can also have these right here, like that. And this is really the more complete picture of this. So let's see, where does cosine of x equal negative square root of 2 of x? So the negative square root of 2 on x, that's it kind of right here. Oh, actually, that's not quite right, because it's the cosine, we have to look at the x-axis. So the negative 2 square root of 2 on the x-axis, that's kind of right here. 2 square root of 2. And then I just project outward and see. And then these are the two rays I should be looking at. So those are the rays of, well, let's see. Well, it's first of all we have to have pi on 2 around, because we have a quarter, and then I do, so this is 2/3 pi, and this is actually 3/4 pi, and this I have done an entire pi, and then I go just a little bit further, and this is 1/4 pi. So those are the two valid solutions. So 3/4 pi and 1/4 pi. So I can just copy those, and then I shouldn't forget the 2 pi times k because again, if I go in an entire circle around, I return back to a valid answer. So 3 pi on 4 is a valid answer, and then add 2 pi times k. And another solution is 1/4 pi plus 2 pi times k. Like that. So those, those are both the solutions to this equation. So I'll just do one more because it's quite complicated. So I'll move it a little bit to the side so I can do a little bit more of this diagram. So let's do sine of x equals -1/2. -1/2. Well, it's sine, so we have to look at the y-axis, right? So I'll quickly note that sine and cosine. So sine -1/2, so it's going to be somewhere here, so it's going to be this -1/2. Oh, I will note that right here, and I can project these outwards again, like that. And so this one, but let's first of all take this one. So again, a step like that, that's just a sixth, right? That's pi on 6, and I have to add 1 pi because I already did like half turn. So that's 1, yeah, I already did half turn. So that's 1/1/6 pi, like this. And actually right here, I could say that this is 1/5/6 pi, but I can also say that this is negative pi on 6. Right, because it works the same, because I have a k that can add once, or rather 2 pi every step. Right, so those are my two angles. So let's plug those in. 1/1/6 pi plus 2 pi times k, or negative pi on 6 plus 2 pi on k. And so lastly, I will look at a specific example. So let's do cosine of x equal to 0. So now we have to see when is cosine of x equal to 0. Well, it's first of all, it's 0 when the angle is 0, right? That's straightforward enough. But it's also 0 when the angle is pi radians around. So let's do that. So pi times k, and x just, well, that's 0 plus 2 pi times k, but that's just 2 pi times k. And let's actually say that we have a certain domain in which we want to evaluate this equation, right? We want to evaluate these x's, and we want to evaluate them at -3 pi to +3 pi, like that. So let's start with this one. When I have a -1 for k, I get pi minus 2 pi, which gives me -pi. And actually, if I have -2 for k, then I get pi minus 4 pi, which is -3 pi. And +1 gives me, or actually just 0 gives me pi, and then +1 gives me 3 pi. And this one gives me -2 pi, it gives me 0, and it gives me 2 pi. So I'm just filling in things for k to see what the resulting answer will be, right? And making sure they're in my domain. Right, so these are my answers, and I'll actually just sort them like this. So -3 pi, -2 pi, -pi, 0, pi, 2 pi, and 3 pi. So those are all my solutions, and you may actually see that this is a bit of a different pattern right here, because instead of adding 2 pi with every k, I'm actually just adding 1 pi, like this. It's add a pi, add a pi, add a pi. So instead of having two solutions, I can actually just combine them to give me one solution. I can actually say that this is just pi times k. Actually, I'm so sorry, this is the cosine, this is the sine. Made a tiny mistake there. But the rest doesn't really matter. It's the same thing. If you have kind of a pattern like this, and you can sometimes combine them into a more compact one answer, or maybe sometimes two, but you can combine them, right? But do be careful when doing this, right? a way to see this visually in the circle is we have 0 as an answer and pi as an answer. And you can see that if I trace half around, I come back to pi, and if I do another half, then I come back to 0. So, and a half corresponds with just pi around, right? So if you trace pi around, you come back to another valid solution. That means you can have this as an answer. Right, so alright, so that basically covers it for trigonometric equations. And I'm actually going to stop it right here. I might do a follow-up video to this, talking about sinusoids and more complicated trigonometric equations and identities. But we'll see. Thank you for watching, and I'll see you. Bye bye.